All right, good afternoon, everyone. We are going to cover the other part of pointers this week. How do we allocate our own memory? So last week we took a look at pointers. How do we make these variables that we can use to point to memory addresses, other memory addresses that we want to? But last week we were only able to point to existing memory addresses. So if something else created that variable, I could point to that memory address. This week, we want to be able to create our own, let's say, variable without a name, if you would, in the heap. And then, of course, if we make a variable without a name, I need some way to reference that, right? So we have a variable, it has an address. How do I point to that? Well, you're going to do it through a pointer variable, and that's how we access that space. So let us take a look. And of course, Wednesday, we're going to do another graded activity, graded exercise, dealing with the topic, this topic. Where am I? C. Oh, that's the wrong class. Here we go. So pointers part 2. This is the other half of pointers, memory allocation. So let's backtrack a little bit. Remember, this is how we create a pointer variable. Pointer variable, we have to declare some data type for that pointer variable so that we know what we're pointing at. So when we dereference it, we read the correct amount of cells. And also so that when we're doing pointer arithmetic, address +1, address +2, we skip the correct amount of cells so that we can get to the starting point of the next element of that data type. So data type followed by an asterisk followed by a variable name. And the addition here this week is that we're going to use a function called malloc. There are other functions you can use that allocate memory. Some do it in different places. Some will allocate memory and automatically zero it out for you. Malloc is the one we're going to look at in here. It doesn't zero anything out. It just allocates memory for you. And by default, the way it behaves is, this is one command, by the way. I split it up into 2 lines because I wanted to make it big enough to read, and it wouldn't fit on one line in my PowerPoint if I made it this big. So imagine this is one line, and to the right side of the equal sign, we're calling a function. Malloc is the name of the function, memory allocate. And what it accepts one parameter. I know I have a couple of things in here, but these are another way I can calculate this parameter instead of giving it a specific value. And the parameter is how many bytes you want to allocate. So for example, typically, if you want to allocate enough memory that you can store an integer, on my system, at least an integer is 4 bytes, I would put the number 4 there because that's how big an integer is. You can, however, use something like this. So this function here, size of, if you give it a data type or a variable, it'll tell you how big that thing is. So now I don't have to know an integer is 4 bytes. I said, malloc enough space that I can store however many bytes big this thing is, times this is how many of those I want to store. So if we wanted to store an array, if I want to store 10 integers, I'd put a 10 here, right? So however big an integer is, and I want to store 10 of them. So integer size times 10, 4 times 10, 40 bytes. And what happens, the way a programming language views the memory, or a program views the memory, even though it's just one physical piece, right, or one physical stick or multiple physical sticks, it kind of logically divides it into 2 pieces. One's called the heap and one is called the stack. We won't go too much into in detail as to what the 2 things do, but for us, the heap is going to be where we put stuff that we manually allocate. So when you want to manually allocate memory, you do that in the heap. All that kind of stuff happens down here. And so when we call malloc, it's going to go down to this region of memory, and it's going to get us some space down there where we can store our variable at. So what malloc does, let's say if we were to use this instruction here, right? Malloc size of int, and int is 4 bytes. If we take that on my system, it's 4 bytes. This is going to reserve 1, 2, 3, 4 bytes of space. And it's going to return to me the address of the first byte. So the address of the first byte in this picture here is byte 6, address 6. And then I would take that address and I'd store it in my pointer variable. So now we can see that X pointer stores 6, but I know how big an integer is. So when I want to read it, I go to address 6 and I read the next 4 bytes. And I'll interpret all of those ones and zeros as an integer. Aside from that, nothing else has really changed. You still use the pointer the same way. If you use it without the asterisk, you get an address. If you use it with the address, you dereference it, and you can go to that piece of memory and either put a value there or retrieve a value. So that's the only difference between this week and last week, is this new function we're introducing, malloc. And malloc will go create a variable down here for us, but it doesn't have a name, so we don't have a way to reference it. So previously we do int x. You know, that'll make a variable and give it a name. It has a name x or int y or int z or whatever you want to call it. Now we have a name to reference it. But this week we're going to create a variable. It's an integer, but it doesn't have a name. We only have an address, and we have to store that address somewhere, and we would do that with a pointer. So that's the only difference between this week and last week. Aside from that, you use the pointer exactly the same way. Here's just another example. Again, we have, I guess I should have written the whole thing out. So here's our heap. I just allocated enough space to store one integer, 1, 2, 3, 4, and I stored, I dereferenced it and put the number 25 here. So that would say, go to that address, address 6, and put the number 25 here. And actually this would be all zeros, 0, 0, 0. And this is where we would put the binary value for 25, because it would fit in one of these 1 byte. I think you only need 8 bits to represent that number. And finally, when you're done, you have to put it back. So you call the free function to deallocate it. So anything that you allocate on the heap, when I make a variable here, it doesn't go away automatically. It stays there forever until you tell it to go away, until you release it or you put it back. Another way to think about it is like checking out a book. So if this is a library and all of these cells are books, every time you call malloc and you reserve a slice of memory, you check out a certain amount of books. So in this case, we check out these 4 books, 1, 2, 3, 4, and that's it. Nobody can use them now. No one else is allowed to use those memory cells for the rest of the program. That's reserved for use with X pointer, or I have to know that address if I want to interact with those cells. That's okay, unless we need more space. So what happens if we keep calling this over and over again? I keep allocating more space. Eventually, I'm going to run out of space on my heap, and my program's going to just crash and stop working. So what we want to do when we're finished with that variable, we want to put it back. We want to deallocate it. Put the books back in, check them back into the library so someone else can use them. Right, so the same idea. We would do that with the free command. You just free and type in the name of the variable. That'll go to that address and release those resources so that you can reuse them somewhere else if your program needs to. And note that your program kind of does this automatically with other variables, with regular variables. But for stuff allocated on the heap, if you take it out, you got to put it back. So here's an example, a conceptual example of what happens, the process here. If I, let's say malloc enough space to store an int. So we're going to point to this first cell in the heap again. First 4 cells. The value of the pointer variable is going to be that address 6. Here I'm going to dereference it and put the number 25 there. So now these cells have a value of 25. And finally, we're going to call free, and I'm going to release those resources. And it's the equivalent to unlocking these cells so someone else is allowed to use it now. So here I just have that. I'm representing that with this X, so that X doesn't necessarily allow me to interact with that cell anymore. It's a little more complicated than that. But at a very high level, we can, for this class, we can just think about it that way. All right. Before I do that, Yeah, why don't we try this exercise, and then we'll look at some examples of this in JGrasp. So let's try this exercise here. And what I'd like you to do, if you have your computers, open up JGrasp, make 2 integer pointer variables. So I don't want you to make int x and y. I want you to make 2 pointers, and I want to use malloc to allocate 2 variables in the heap. And you have to save them into your pointer variables. And then, of course, you have to dereference to use them as whole numbers, you know, put some values in there, add them together, and then free one of them and try to add it together again and see what happens. We can do some of this together. Let's make a new file. Oh, and to use malloc, you need to include, sorry, I forgot to mention this, you do need to include a standard library. So that's not included by, that isn't included in by default. In C, it's also not in the input output library. If you want to use malloc, you need to include this standard library. That function's included here in that library. All right, so someone get us started. Let's just start by making our two variables. We'll do it in separate steps. We'll just declare our pointer variables. How can I do that? How can I declare two pointer variables? That's all I want to do for now. Okay, so int x, and then we can just make another one like that, right? So int, and then two pointers. Now, how do I, let's do one of these. How would I allocate enough space to store one integer? I want to allocate enough space on the heap. I can store one integer and I want to save that address into X. How do I do that in C? So I want to create a variable in the heap. And then I want to save that address into one of my pointer variables. Very good. So we can do size of int. And we only need one of them, so this is good enough. And we can check something real quick. Let's just do print, just so we can see what big, you know, how big is an integer on my computer. And it is size of int, and this should tell us how big an integer is, and you'll see that's the number it's passing in here. So it's going to return that number. Right, so let's compile it real quick and we can run that. That's fine. So run it, and you can see, sure enough, okay, an integer is size 4. So this is actually, this is the same as writing the number 4, right? These two mean the same thing. I could have just put a 4 right there. If I knew that. Another reason we want to do this is data types are not the same size on every system or with every compiler. So it's better to do something like this, where you let the system calculate what the size is and it tell you what it is. So now I have enough space. This function will go to the heap and reserve that many bytes for me. It'll make a variable that's that big and it'll return the address to me. And I'm going to save it here. So why did I do this? Why didn't I do that? Why didn't I dereference it when I did that? So what you're saying is how dereferencing works, right? So how does dereferencing work? That's what you're trying to. You're on the right track. You're just not using the right words. Yes, in the back. Very good. So dereferencing says whatever address is stored in here, go to that address and use that cell, right? So if we go to our PowerPoint, but you're both saying the same thing. So dereferencing this, if I dereference that, it says go down here and use that, versus like this is X. X is up here, right? My X pointer is actually right here. Or that should be right here. It should have the value 6. I forgot to include that here. Sorry. But that's what dereferencing says. Now, the other issue is I don't have an address yet, right? What is the address of X pointer? Well, I don't have one right now because I haven't saved an address there yet. By default, it should be null. And depending on the system that's implementing it, that may or may not be true. But by default, it should be null. So very good. We want to use it like an address variable because we are trying to store an address. We don't want to go to an address and do something. And we would do the same thing with Y, right? We could just copy this. And so you all work a little bit more. The next part, we want to do what? We want to add some values to those, add them together, and then free one of them and see what happens. All right, have we got some values in X and Y? We should X, Y, we can just make it 10, 20, and 10. And if we were to add them together, how would we add these together? So I know they're both numbers or whole numbers. Print a whole number, and then we want to add 10 and 20 together using our pointer variables. How would we do that right here in this statement? Let's get someone that hasn't answered yet today. Yes. Very good. So dereference X plus Y, and we should get 30, right? So if we print this, we should get, sure enough, we do get 30. Now, if we free one of these, leave this section, we'll come back to that. So free, right? We're just going to free, and then we put the pointer variable name. Remember, we're not going to use the asterisk. We're not trying to dereference it. We want to use it as an address variable, and then try to do the same thing. Let's see what would happen. What should happen, it should just give us back the value of the other one, because this should not work anymore. So it should get interpreted as a 0. And sure enough, let's actually do a new line here. And here we go. Sure enough, we get back the value 20, because once you free it, technically we've given it back. We're not allowed to actually use that address anymore, right? So it's going to return null. It'll return 0 for X, and then Y is just going to be 20. So 0 plus 20 is going to be 20. And just a side note on what we did here, we did a little of fudging with the language here. So we made a character pointer, and remember, pointers just point at addresses. So we don't really care about data types. And I pointed it at X. So a character, just a little bit of information, and see, a character is 1 byte. So we know integers are 4 bytes. So if I make a character pointer and I print 1 byte at a time, right, then I can print all the ones and zeros in each of the cells. So just so you can see how this looks in memory, right? So the value 10 in binary is 1010. So if you have 4 bytes, 1 byte is 8 bits. So it's going to be 4 zeros and 1010. That's 1 byte. And the rest of them should be all zeros. And if you print each character, so you print all 4 bytes, what do you see? You can see 0, 0, 0, and then that's 4 zeros and 1010. Does that make sense? I see some like confused faces. Maybe I should have left that out of it, huh? So what I was trying to do was show you, what these cells look like. So I have an integer pointer that pointed to this first cell. I made a character pointer, because an integer pointer, if I read that, it's going to scan all 4 bytes. If I make a character pointer, it's only going to scan one of these. And then I can just print 1 byte at a time, just so you can see what the contents are, so you can see what it actually looks like in memory. I think there's also a way that you can print the binary value of that thing too, but we don't want to do, we're not going to do it go that deep in here. All right, moving on. So here's something you have to be careful with. And remember what we said about how malloc and the heap works. If you allocate space in the heap, it will never go away until you free it. That's not necessarily a bad thing, but let's say now that you call a function like this, test pointer, and in this function, what I think is happening, I think I'm passing in an address, and I think I'm going to get to keep that address, right? Because I'm going to call malloc, save it into that variable, and do this stuff. And if I never free it, or let's say here we do free it, but if you don't free it, what happens is that memory gets allocated. And since this is actually a copy of an address, you don't get to keep that copy. So that gets reserved and it never gets freed. And every time you call this function, you're going to reserve more space. and it's not going to get freed, and you're going to reserve more and reserve more and reserve more. And again, eventually you're going to fill up that heap and you won't be able to, your program's just going to crash. So if you are typically, if you're going to allocate memory in the heap, if you're going to be using malloc inside of a function, you typically also want to free it right there. You don't want to try to free it from somewhere else. What do I mean by that? So let's take this here. We'll make some more pointer variables. Int pointer pass me. So I'm going to pass this pointer around. And what we think we're going to do, we think we're going to allocate memory for it here. Actually, we can remove this for now. We don't need this. Less stuff is better. Void, we're not going to do anything. I'm going to say mod pointer and int pointer. And here, what we want to do, we're just going to allocate something over here. So pointer equals malloc. We'll do it the same way that we would use we'll just do 4 because we already know how big it's going to be. That's an integer. And that's all we're going to do. So we can actually set it to a value. Pointer equals 22. So let's do that and try to print it. We're going to create that variable. We're going to call mod p, and we're going to pass it that variable. And then we'll try to print it and see what happens. All right, so what we think is happening is that we're passing this pointer variable into this function. We're allocating, we're going to create a variable in the heap and save the memory address, put a value there. And then this should point to that heap variable, right? It doesn't if we, why is it still telling me that? Oh, not save it. There we go. So if we run it now, we can see what happened. My process died on signal 11. Well, that's interesting. What happened here? Let's try to print, let's do print a before and after. Okay, so let's print the address of that, whatever that's stored. %p prints addresses, prints pointers. And we'll do pass me. And then after we call the function, we'll do that again. And see what happens. So compile it. And we can see, sure enough, actually this was null. It never had an address. In here, we can do this too. Just so you can see that it did actually have an address at one point in time. So you can see inside the function, we allocated that, it had an address, we set the value. I could have printed 22 in here, but now outside of here, we can't actually see anything anymore. That didn't happen. That didn't, let's say, return anything, right? So what happened was here, what we actually did was we made a copy of this value, which is null. So we made a copy of null and we copied that into the function's address space. Remember, function still can't see across those lines. So I didn't actually pass an address down. I passed a copy of nothing. And then inside the function, I set that, but this is temporary. So once the function goes away, this goes away too. And this never really changed. So that's what happens. So you got to be careful when you're using pointers and functions, specifically if you're using malloc in a function, right? So that's going to allocate that space and then it's going to be gone. Now, what could I do? Is there another option? Can you think of another a way I could actually save this value, do something with this? What's that? So I could allocate the space. I could allocate the space here and just give it an address and let it go modify that space. That's one thing to do. Or, in C, you can return pointers. So I can just return an int pointer if I want to. Right? And then, honestly, we don't even need this anymore. We can just we'll make one here that's going to go away anyway. It's temporary. So int pointer And when we're done, we'll just return that, we'll return that variable. And now here, right, we don't need to call anything anymore, or we don't need to pass it anything. So now we're going to generate that address, and we're actually going to give it back now. So we're going now it's okay. I can allocate that variable in the heap if I want to, because I'm giving the address back. So now it's okay to do that. If we run it, we can see now I do have an address when I come back, and I have the ability to notice it's the same address, right? Because I returned it, and I actually can access it and print it as well. So the moral of the story, you got to be careful when you're using pointers, specifically malloc, inside of a function, okay? Because of how parameters and output work. In general, unless you plan on returning that pointer, if you allocate it in a function, you need to deallocate it in the function also by calling free. And we talked about the fact that we could create multiple, we can allocate multiple, enough space to store multiple of a data type, right? So that would be, the equivalent of that would be an array. So what is an array? An array is a data structure that can store multiple copies of a specific data type. So you can store multiple integers, multiple characters, etc. You can do the same thing with pointers. So when you call malloc, instead of saying malloc enough bytes to store one integer, I could say, well, maybe I want to store 10 integers, right? So it's 4 times 10. And instead of saying 4, I could say something like size of whatever my data type is. Here it's going to be int times 10. So what is this saying? I want to store 10 integers. That's how much memory I need. That's how much space I need. And it's going to work the same way. I'm just going to pass back the starting address. And as you've seen, well, I don't have it here, but as we've seen previously, you can use either array syntax or pointer arithmetic to access those elements. So when you use it that way, one way people commonly refer to this is a dynamic array. This is dynamic in the sense that with a regular array, everything is fixed, right? Typically, when you make an array, the size is fixed. You can never change the size. That's it. And that array variable always points to that memory location. But with pointers, you can create the equivalent of a dynamic array that you can resize at will. And how do you resize it? Well, you can resize it because it's just an address variable, and you can point to a different address that stores a different amount of things, right? So here's an example. Here we're going to allocate enough memory to store 10 integers. We are going to put some values in that location. We're going to print each of those items. And I don't have an example of resizing it. So if I wanted to resize it, all we would do, we would just allocate a different amount of space, more or less, copy the original into the new, and then change our pointer so it points to the new thing. So we'll take a look at an example of that. Let's take a look at an example of that here. We'll do this in just a minute, but first let's look at an example of what I'm talking about, because it's a little confusing, I think, to just talk about it and not give a concrete example. So what do we mean? Let's do this. Let's say int dynamic array, right? So I have a integer pointer. My variable name is dynamic array because that's the way I'm going to use it. I'm going to use it as if it were a dynamic array. And here, we'll just, well, let's make a small one. Have it so it can store 4 numbers. And we'll put something in those cells. So we'll make a pointer and an I. So it'll just be 1 through 4, right? So if we do this and we print it, I guess I should have used let's not do a one-liner We want to do other stuff. And just so you can see that we can use array syntax or pointer arithmetic. We'll use both of them here. So we're going to use pointer arithmetic to put a value in it, and we'll use array syntax to print the value. Either one is fine. They're both acceptable in C. And if we run this, what do we see? We just 1, 2, 3, 4. That's what we put in here. Now, what if I needed more space? I want to put another value in here. If this were an array, too bad. I would have to make another array. This space would never be unused. It'd just be used forever, as long as I'm in main anyway. And I have to make another array and use that larger one. So I take up, potentially double the amount of space. But with dynamic arrays, what I could do, I could make a let's make another, we're going to allocate another variable in memory. Malloc size of int, and we'll do times 8. So we'll double the size. So I can store 8 integers now, doubling the size of my array. And I have to, as soon as I free the original array, I'm going to lose that stuff, right? So before I lose it, I need to copy those values in. So we'll just go through our loop again. And here, let's use array syntax. It's a little easier to, shorter to type. So we'll do temp I equals dynamic array I, and then we'll just print just to make sure we have the same stuff. So sure enough, they're equal now. I copied everything from the old array into the new one. But unlike previously, now if I want to, I can go and free the original one. And then we can do this. It's just an address, right? It's just an address variable. Now you equal that. And then I can set that address to null. I think it needs to be capital. Let's see. So basically what we've done is now we've released the original location, but we've conceptually, we've dynamically resized the array. We can grow it or shrink it if we want by just allocating more or less space, copying the old stuff into that new space and getting rid of the old stuff. Right, so this is something you can't do with regular arrays. You can't ever get rid of the original array. So technically you're not resizing it. Technically you are making a new variable, but conceptually it's the equivalent to resizing the array. So that's why hence the term dynamic array. So if we were to do this, then we could see, now let's just do, let's do our for loop again. And this will go to 8, right? And we'll just print that. Of course, we never put any values in the last 4 cells, right? So, but that's fine. It should still have, right, 1, 2, 3, 4, and oh, it looks like they were one behind the other. So the contents of the other array must have been immediately after it in memory. So it just printed 1, 2, 3, 4 again. That's what you're seeing down there. Oh, no, it's not. I didn't put a new line. That's what that is. Hold on. This is the new array. It's 1, 2, 3, 4, and then 0, 0, 0, 0. Let's do this. There we go. Very good. So we can see, sure enough, we have dynamically resized our array to make it bigger, to accommodate more things. So we still have a couple of minutes. Let's try this exercise here. What I'd like you to do in this exercise is write an interactive program that'll prompt the user, how many things would you like your array to hold? And this is another thing you can't do either. Is on the fly dynamically create an array of a specific size, right? So in your program in C, this stuff is kind of fixed at compile time. But with pointers, you can just dynamically create an array of whatever size you want. So I would like you to prompt the user, capture that input, and then make an array that big, a dynamic array. Use a for loop, kind of like I just did here, to put some random values in it. Use another for loop to print the values out. And then, of course, when you're done, don't forget to free the array, right? And let's do some of this together. We'll reuse this. So prompt the user, we'll just write a printf statement, right? How many things, how big is the array? Let's do, how big is the array? How big should it be? All right, so we're just going to print something, some message the user is going to read so they can enter a value for us. And we'll save that somewhere. All right, scanf. We're going to save the whole number, and we're going to save it right there, wherever size is. And now we're going to create our dynamic array. So, or we're going to, we're going to create that variable in the heap. So dynamic array equals. What are we doing here? So how big am I making my array? What am I doing? So we need to call the function that's going to create a nameless variable for us in the heap. And that will return that address to us. What function are we using to do that? Malloc, very good. So Malloc, and how does this function work? I need to store this many things in my array. So something like this, size of int, and then size like that. You got to multiply them together, right? Because this gives you back a number, and that's also a number. So if they tell me 5, that is the equivalent. Let's just and sometimes it's helpful to actually write out the values of things instead of using the variables. That would be the equivalent of typing out 4 and then a bunch of spaces and a 5. That's actually 2 parameters that aren't separated with a comma, right? So this wouldn't work, but if we put this in the middle, now we have an arithmetic operation that it can perform and return a value, right? So 4 bytes, because that's how big an integer is, and that's how many of those things I want. So 4 bytes times 5 is 20 bytes. That's how much space I need. Very good, very close, very good. So this times that, that's how much space I want. And then we'll use a for loop to populate it. What do we say? All right, so for 0 I less than that, because that's how many things are in it, I plus plus, and we'll just put some, we'll just do 1 through whatever size is again. So dynamic array, and we can use array notation or pointer arithmetic, either one is fine. equals I plus 1. And we can go ahead and print it here as well. All right, so let's compile this and let's run it. And how big is the array? Let's just make it 10 spots, and there we go. All right, we can run it again. 20, very good. Run it again, 100. So we can see now we can dynamically create an array of almost any size we want. There's a limit, of course, how much memory you have. So there's a limit how big you can make it, but we do have the ability to dynamically, every time we run this program now, we can dynamically create an array that's a different size. And then, of course, what did I forget? What did I forget to do? I forgot to free my array. Very good. I have to release those resources. Now, conveniently for me, as soon as that's done, the program goes away. So that's the same. It's going to release it anyway. But it's still good practice to do it. You should still free it just out of habit. So how could you extend it to this? This is probably too confusing. A 2D array is if you want to implement it completely dynamic, it's a pointer of pointers. So you have to malloc enough space to store 10 pointers. So you're going to have an array of pointers. And then you have to go through each of those pointers and store enough space for whatever that item is. So what you see, we'll leave this here. You all can look at this on your own. I don't want to confuse you. For those of you that are interested, here's an example of how you could make a completely dynamic 2D array where you're using pointers for everything. And you see, once you've done it, you can use pointer syntax to reference it. Or you can use pointer arithmetic. If you want to use pointer arithmetic for 2D array, it's actually really, really confusing, which is why I chose to do this instead. So we'll leave that as food for thought for those of you that want to pursue it. I'm not going to try to explain it here because I don't want to confuse anyone. But just a quick recap. What we talked about today, we talked about using the malloc function to create variables in the heap. They're nameless variables. They don't have names, but all variables have an address, and the malloc function will return that address, and we can save that in a pointer variable and to reference that variable in the heap. This memory that you create in the heap can only be accessed through pointers. That's the only way you can access this memory. You have to use a pointer variable. If you do decide to do that, it's your responsibility to manage that memory. You're responsible for that memory now. The computer is not going to manage it for you anymore. So if you got it out, you got to put it back using the free function. And then, of course, we talked about dynamic arrays. You can create conceptually the equivalent of a dynamic array, at least in terms of the size and amount of things you can hold. You have the ability to dynamically resize this type of array. You can make it bigger, you can make it smaller, you can move it around, and that's something you cannot do with a regular array. And then, of course, as we've mentioned several times, if you're dealing with dynamic arrays or pointers in general, you can use either syntax. You can use array syntax for pointers or vice versa, right? So you can use either pointer arithmetic or array syntax to interact with pointers or arrays. Of course, there are some subtle differences. There are some limitations to that, but for the most part, that's an accurate statement. And that concludes that chapter. Do you all have any questions for me? All right, see you on Wednesday for the in-class exercise. Have a good day, everyone.